I've started to get a couple of questions about the homework that's due next Wednesday, so that's good. You're hopefully getting an early start on that. Selena noticed a mistake in the homework assignment. On one part of the homework assignment, I say that in the table it says NB VSS is 40 milligrams per liter, but then in part A I say assume no nitrification and NB VSS equals 0. And so go with what it says in part A. Assume that NB VSS does equal 0. In that part. In part A, what I'm doing there by saying assume it's 0 is I'm simplifying. If you look at the equations, you'll see what that simplification, what the implications of that are. So, all right, 2 weeks from tonight is our last class of the semester, and your research papers will be due. And then on Wednesday the 6th, we'll have our final exam. That'll be shorter than usual for the final exam. You know, we have scheduled 3 hours. I guess we have scheduled usually 2.5 hours. I don't even know. When do we usually finish? 8 o'clock? That's 2.5 hours, right? Okay. The exam, I'm going to anticipate writing a 75-minute final exam, and you'll have up to 90 minutes to take it. And if you really do need more time, I suppose you could use it. But I don't think we'll be here the full time on the 6th is the bottom line. Today we are continuing in our quest to understand secondary treatment, and in Chapter 9 it talks about attached growth and combinations of attached growth and suspended growth. So before we get into that, are there any questions related to the research papers or the homework? Next week I'll give you some additional information about the final so that you can start studying for that. The final in some ways will be a little bit different than how we did the midterm exam. And we'll talk about the differences and the similarities. So.
We're back the 29th?
Yeah. Okay. What we're looking at is a variety of different combinations of both suspended growth and combinations. We're going to go through each one of these different types of configurations tonight one by one and talk about some of their similarities and differences. But just to give you an overview of maybe what's unique about attached growth is that it's possible in some cases to have considerably more efficient treatment, meaning a lot less energy expenditure for the removal of BOD. And so that's at one end of the spectrum is much more economical. And then at the other end of the spectrum is improved effluent quality when you combine activated sludge along with attached growth. So here are some pictures of kind of the old style of attached growth. These are trickling filters with rock media, and we've talked already briefly about trickling filters. They can vary in size from relatively small. You can tell just by the ladder going up to this. You know, obviously the ladder is probably about 1.5 feet wide, so that trickling filter isn't very big. And then this trickling filter happens to be 50 meters in diameter and 10 meters tall. And so it's enormous. In that particular facility, they've got 4 of them that are that size running together in parallel. So they can really cross the whole spectrum of everything from small to big. And they're not very common for a couple of operational reasons. And partly because there's a perception that they are more fickle than activated sludge systems. The perception that they're harder to fine-tune and manage. But just to kick things off, I wanted to show you a video about trickling filters. Turn on the speaker so you can hear that. If I remember correctly, there's no good music in tonight's videos, so I feel bad to disappoint you on that. But the video itself is pretty good. This trickling filter is in Utah, and I've actually visited the treatment plant where this video was taken. And I don't know if you could hear what he just said, but the person who's sort of giving the tour mentioned that there's no electric drive for this that's rotating the arms, that the arms are actually driven strictly by the jet of the water that comes out of that discharge assembly. So we're going to kind of do a little bit of critical thinking tonight, and let me ask you a question. Why do you suppose the arm... All right, I'm going to pause it right there. Why do you suppose they don't have sprinklers that are fixed, just constantly spraying rather than rotating around and every once in a while discharging water? Why not have like a fixed sprinkler that's just spraying on top of it? Sure. Okay, but you still could potentially get equal distribution if you had, let's say if we had a tank and here's a sprayer and it's just always spraying the water down. Let's say that we overcame any sort of problems with equal distribution and we're wetting the entire area continuously. There's still a reason why periodic wetting is preferable to continuous wetting. Any ideas or thoughts about that? Okay. Yep, part of it is that, remember, in secondary treatment, the bacteria need the substrate, and here, what we're spraying on the bacteria and the rocks that the bacteria are living on, we're spraying water that's already been through a primary treatment, and so much of the suspended BOD has already been settled out, but the dissolved BOD is still in the liquid. So we're spraying water on them, but the way they get their air is, in a lot of cases, like in this case, there's no external blower. It's just natural passive ventilation that's going up through the rocks. And so if it was continuous spraying, it wouldn't get the same opportunity on the surface of those rocks to be in direct contact with air. The water that they're spraying has a little bit of dissolved oxygen in it, but the bacteria that grow, it's like a slime layer that grows on the rocks. It works best if it has direct contact with the atmosphere, and so it sprays the water and then it dries for 15 or 20 seconds, then it sprays, then it dries, and so it's a continual wetting, and it doesn't go all the way dry, but it's a wetting, air contact, and so that's partly what it's related to. But that's not the only thing. We'll talk about the other operational reason why periodic wetting is important as well. But I wanted to just address that to begin with to set the stage that oxygen contact is important in trickling filters, and dissolved oxygen concentrations aren't enough for providing the oxygen in the on the surface of the rocks. So you're not going to get all the oxygen the microorganisms need just from the DO of the liquid itself. Typical depths for the rock bed are between 3 to 8 feet. And of course, I mentioned when we were looking at this in the earlier section of the course that you can get much deeper if you use a plastic media because it's not as heavy. And you can also have quite a bit more variety in terms of the microbiology that's present inside of a trickling filter. There will be bacteria, including nitrifying bacteria, down towards the bottom of the trickling filter. And the nitrifying bacteria set up at the bottom of the filter for the same reasons that they only selectively grow where they have a competitive advantage. At the top of the filter, the BOD concentration of the liquid is higher, and there are other microorganisms that outcompete the nitrifying bacteria. The nitrifying bacteria are they have slower kinetics, and so they grow where other bacteria don't want to. Not that they don't want to, but the other bacteria higher in the filter, closer to the source of the substrate, have a better advantage there. One of the problematic things that can happen is that the pores between the filter can clog. And remember, in activated sludge, we're mixing the aeration basin quite vigorously, pumping in a lot of oxygen or using a mechanical aerator to stir things up. And so the particles that are suspended, there's really not a risk that there's going to be a clog. But in the case of trickling filter, especially during periods of low flow rate, in the middle of the night, if you think about how slow that arm would be moving in the middle of the night if there was a very low flow rate and they didn't recirculate to try and keep it moving, it's possible that either the bacteria could dry out and be killed for that reason, or that during other periods the bacteria could grow so quickly and the slime layer could actually clog. There are pests that can grow in trickling filters, and usually these snails or worms that it's mentioning, they consume the slime layer. So they're sort of like secondary predators that live on the bacteria, and particularly the nitrifying bacteria, because they grow so slowly. We wouldn't necessarily mind the snails and worms being in the trickling filter, except for the nitrifying bacteria that grow so slowly get consumed quicker than they can repopulate when snails and worms are present. Because of the way oxygen diffuses into the slime layer, only the outside of the layer is aerobic, and the interior of the slime layer is anaerobic, and that does provide some limited opportunity for nitrification within the slime layer. Here you can see sort of a cross-sectional view of that of the filter bed that we were just looking at, similar to it. And you can see at the bottom of the filter bed there's a support media. So the rocks aren't just put on top of, like in a concrete swimming pool. They're resting on kind of a structure that supports them so that water can be collected at the bottom very easily without having to have a stagnant pool of water at the bottom. That would be actually pretty bad, because the slime layer would slough off and get stuck at the bottom. And so you can see this support structure that's at the bottom. That's really important for allowing the bacterial particles that fall off of the rocks. They go down into the sort of the trench underneath the media, and then they are swept towards the outside and settled in a secondary clarifier. Sloughing, this word sloughing, is something that varies a lot through the seasons, especially in rock filters, because in the spring, when the bacteria start to grow more quickly, they can grow faster than they were over the winter, and the biofilms are mechanically dislodged. And by mechanically dislodged, what we mean is that this wetting, let me go back to the little image here of the video. As this arm goes over, it's a typical practice in a trickling filter to have a period during the day where you turn up the flow rate pretty high and kind of scour off the rocks a little bit. It's sort of like a cleansing run where for a few minutes they'll have a really high flow rate to try and induce an intentional sloughing of the slime layer off of the media. And that can happen in the spring just because all of a sudden the microbial balance is changing as it warms up. And so that's why they say it's a seasonal phenomenon. And then how much sloughing occurs depends on the organic load of the waste and how much recirculation is happening and so on. Now, if we compare attached growth to the traditional suspended growth that we've been talking about for the majority of the semester, the big advantage is that it's so much less energy intensive. And just to give you a ballpark, in terms of kilowatt hours per cubic meter of wastewater that's treated, an attached growth secondary treatment like a trickling filter may only use 1/4 of the electricity of a typical activated sludge. So if you think about the car that you drive, if you were able to get a 4-fold improvement in fuel economy, instead of 1 gallon getting you 50 miles in a Prius, what if 1 gallon of fuel could get you 200 miles? Or you probably don't drive a Prius, right? Probably drive something with a little more horsepower than that. But think about 4 times better fuel economy. That's sort of the scale of improvement that you can observe with attached growth. It's also simpler because one of the things, it's a point of flexibility in activated sludge that the operator is able to, through wasting of the sludge, control the concentration of mixed liquor in the aeration basin. And so, the operator is trying to decide each day, what do I want my solids retention time to be? Therefore, am I going to increase or decrease the concentration of suspended solids in the mixed liquor? And so they're always sort of doing this balancing act of trying to find out what's the concentration and what should it be. In the case of attached growth, there isn't any recirculation of the sludge solids. The biofilm that sloughs off is just settled and the sludge is disposed of. There are a few rare instances where they do recirculate the biofilm, but in general, it makes it a lot simpler if you don't have to worry about balancing out sludge solids like you do in an aeration basin. And then the other thing is that you don't see the growth of filamentous organisms. Remember, we talked about bulking sludge, and sludge volume index is the way of estimating how much volume sludge is going to occupy after it settles for a period of 30 minutes. Well, the slime layer sloughs off and settles very well, so it has excellent settling characteristics. And for that same reason, the sludge thickens better. And we've talked about where is the majority of the expenses in wastewater treatment. And probably at the top of the list is electricity, moving water from place to place, aerating the secondary treatment. Another one of the big expenses is dewatering sludge. And here in Huntington, when he was saying that on average, I think he was saying that they have 4 truckloads of sludge going to the landfill each day. And so if you were able to concentrate a sludge from 1% solids to 2% solids, that would cut the volume of sludge in half that has to be disposed of. And that's about the scale of improvement one can get with a good settling sludge, like you'll see with suspended growth, is better sludge thickening, and therefore it's less expensive to get rid of the sludge. Shock loads is another thing. We've talked about how a shock load is suddenly there's a huge pulse of BOD, or maybe there could be a toxic substance from an industrial wastewater that gets discharged into the waste stream. The outside of a slime layer may be exposed to a toxic substance and die, but remember, the slime layer can be up to 10 millimeters in thickness, and so it's sort of the interior layers are insulated from what's going on at the exterior. In contrast to that, in activated sludge, the particles are very small, and so they're intimately exposed to the water that they're floating around in. And so a shock load isn't going to do as much damage in attached growth trickling filter than it would in a traditional aeration basin. But it's not all happiness and roses. It's not just advantages. There are some problems with trickling filters and other attached growth as well. In general, the effluent isn't quite as good. A lot of times, attached growth is used as a first draft of secondary treatment. You'd have to have 2 of them in series or already a pretty dilute waste to have effluent that's good enough to discharge into a stream. So the effluent's generally not as good as the quality that you can get from activated sludge. And because the air is blowing through it, it cools off more quickly. You know, a tank of water, we all know that water holds on to a lot of heat, and that's why it's the heat from the ocean that warms up Western Europe. You know, Western Europe is at a pretty high northern latitude, but it stays warmer than it otherwise would because the currents are taking heat from the equator up towards northern Europe. Just water holds on to heat longer than air does, and so overnight when it gets cool and that cold air is blowing over the filter media in attached growth, then that'll slow down the rate of removal even on a daily basis, and then of course through the seasons as well as it starts to cool off. Also, if you're blowing air, or if air is just naturally percolating through a filter media that has wastewater sprayed all over it, obviously you're going to get some smells from that. And so where people are living in close proximity to trickling filters, you have to account for the fact that odor production can be pretty significant, especially sulfur-containing wastewaters tend to have a lot of odor production. Removal of nutrients is more difficult because it's harder to control the environment within the filter, whereas in an activated sludge you can put small, short duration contact basins where you don't aerate and create conditions where removal of nutrients is a little bit easier. So there are some disadvantages that have to be accounted for and sometimes overcome, but this figure shows some of the range of performance that you get from different configurations. And a roughing filter is one where it's just being used to kind of take the edge off of the waste, just to reduce the BOD before the water goes into another treatment process. And so on the right side of this table, a roughing filter is one that we don't expect to have a lot of removal. And if you look at the removal efficiency, it has the worst performance of all the different columns. It's saying between 40 to 70% removal. Now that's nothing to sneeze at. If you can get half of your BOD removed using a filter that uses, in some cases, almost no electricity, then that's definitely worth doing. And so where trickling filters and activated sludge are used together in series, then a roughing filter would be a great investment. If you have a low or standard rate filter, the rate that they're talking about is the loading rate. And so all of these are saying intermediate rate, high rate, high rate. So the rate that it's referring to, if you look at the organic loading is increasing from left to right. And the units of this are how many kilograms of BOD per cubic meter of water per day is loaded through the filter. Kilograms per day of BOD. And they also have just one column that indicates the performance of plastic. And what you'll notice is that in the case of plastic, that the BOD removal efficiency is a little bit better than if you're using high rate rock. But the real difference is how much higher the hydraulic loading can be. And so from 10 to 40 cubic meters per day per square meter of area versus all the way up to 75 cubic meters per day of water for every square meter of cross-sectional area. Now, here's the figure where it says typical activated sludge uses between 50 and 150 kilowatts per cubic meter per 10 to the third cubic meter of water that's being treated. And so here is the power requirement. The equivalent power requirement, the last line for some of these trickling filters. You can see in the case of low or standard rate, it's only using between 2 and 4 kilowatts per 1,000 cubic meters of wastewater that's being treated. And so, you know, at the worst, the case of a roughing filter is maybe using up to 20, and the best case scenario for activated sludge is 50. So it's between 10 times, maybe 20 times better performance, at worst You're getting a doubling of performance as far as the energy consumption. And so this last line, in my mind, kind of says the most out of everything, is that if you can get BOD removal for such a low amount of electricity use, then it's really something to be considered. Okay, filter loading rate is, there's two ways to look at it. There's the hydraulic loading rate and the organic loading rate. And so let's look at the units again. Hydraulic loading rate is cubic meters per day per square meter of filter area. And so let's think about the water that's going in, Q, as units of cubic meters per day. And then here's the filter area. You know, if it has some certain diameter, then we could calculate the filter area is going to be pi d squared divided by 4. And so it's going to have units of square meters. So the hydraulic loading rate is going to be Q divided by A. And that's where the units of cubic meters per day per square meter come from in the hydraulic loading rate. In the case of organic loading rate, it's a similar thing except we're looking at the mass flow rate of BOD, kilograms per day, and then it's going to be cubic meters of volume in the filter. And so if we have a certain filter height, here's the height of the filter, then the volume would be the area times the height. And so the organic loading rate is how many kilograms per day of BOD are being loaded per volume of filter. During the overnight hours, recirculation has to either be used or you have to have a flow equalization basin to try and even out the peaks of high flow rates during the day and low flow rates at night. And so in a low rate filter, you've got a really big area, a very, very big diameter in a low rate filter. And they have to do recirculation there at night just to simply keep the filter packing wet. Recirculation is used for different reasons on different types of filter. In the case of an intermediate filter, they may be using recirculation to try and keep some of the nuisance pests out of the filter. And then in the case of a roughing filter where it's being used just to remove BOD before it goes into some other treatment process, then you may not need to recirculate at all in the case of a roughing filter. One pass might be able to get you the reduction that's needed. So look at these different alternatives of configuration. In the first, you can see that there's recirculation of the water, and there's going to be a little bit of a slime layer in here because, you know, when it sloughs, when the particles slough, the water's moving through the bottom of the filter into the pipe. So what's recirculated will have a little bit of slime layer in it, but it hasn't been concentrated before it gets there. In this option B, what little sloughing has occurred hopefully gets settled out in the primary clarifier. So you can see they're recirculating the overflow or the underflow from the trickling filter and putting it through the primary clarifier first. This would just be to try and further improve the fact that the trickling water that's added doesn't have any of the sloughing slime layer in it. Having filters in series like this improves the performance. And an example we're going to work tonight using rock filters, we'll have two filters working in series. And you can see that there's a waste sludge, an optional waste sludge recirculation that can happen between the secondary clarifier and influent to the primary clarifier. And then, but in this case C, there's no clarifier between the first and second stage of the trickling filter. And this last configuration that's shown, they do put an intermediate clarifier in just to ensure that there isn't any slime layer being recirculated into the second downstream trickling filter. Nitrification is more difficult to achieve in a trickling filter because nitrification, denitrification, remember, is an anaerobic process. There has to be a lack of oxygen to have the conversion of nitrate into nitrogen gas. And so it's a little bit more difficult to have that, except for the fact that the outside of the slime layer is anaerobic, the inside of the slime layer can be, the outside is aerobic, the inside of the slime layer can be anaerobic. And so very low concentration of BOD favors the growth of nitrifying bacteria because bacteria that break down carbonaceous material, they prefer a higher substrate environment. And really, the BOD has to be below 15 milligrams per liter before the bacteria that grow on nitrogen are going to be able to take over and get the concentration of nitrogen low enough. Traditionally, rock is the media that's used for trickling filters, but lately there have been the development of a lot of proprietary filter packing media, and so I'm going to hand some of these around. Dr. McCormick gave these to me. They were his for a long time, and when he retired, he let me have his filter packing. So the two clear ones have never been used before, but the green one has. It's actually got some dried up slime layer on it. I don't know how long ago it was in a wastewater treatment plant, but I've handled it before and I didn't get sick, so hopefully none of us will. What they're going for in these proprietary filter packing systems is just trying to increase the surface area because the slime grows on the surface of the media, and so the rock, the inside of the rock, isn't doing any good. You want to try and maximize the surface area, but there's a limit because if the slime layer itself is getting up to 10 millimeters thick, then you can't have a really, really small structure for it to grow on, or else the slime layer is going to intercept itself, between the layers of the sandwich board here, for example, and so there has to be something for the bacteria to adhere to. It can't be too slippery of a surface. Also, they are trying to have a very lightweight material so that they can make it taller without having to have a costly support mechanism at the bottom. So lightweight, high porosity, durable, something plastic that's going to be resistant to corrosion, and so on. Rock is very heavy, and you can see that if it's a small river rock, it's cheap because you're not having to buy a plastic composite. You maybe can just get it from a local area where it's being built, but because it's so heavy, that limits how tall the trickling filter can be. Also, if you look here in the application column, this is a table from the textbook. It shows where nitrogen removal is possible, where the removal of carbonaceous material is possible, and you can see that actually all of these have the potential to remove nitrogen, and the improvement of these plastic filter media is the surface area is so much higher. 150 square meters of surface area for every cubic meter of volume. So that's more than triple large river rock, you can see, which is at 45. So that's one of the key reasons, in addition to it being lightweight, and so you can make it taller, is that the surface area is so much higher. Okay, we talked already about hydraulic loading rate, and part of how they decide how much to recirculate is looking at how quickly they need that arm to come through so that the rock media is kept wet. And traditionally, you want to have a revolution every 30 seconds to 2 minutes. That's just sort of the typical the typical thing is to have the arm rotating so that you have a revolution every half minute to every 2 minutes. And so if there are 4 arms on it, that would mean you're getting the rock wetted 1/4 as frequently as the total transit time for 1 revolution. So what we saw is, it looked like it was probably making 1 revolution in, I don't know, a minute and a half or so, and so there's 4 arms. I don't think all of the arms were wetting, though. If we look at this one's spraying, but that one isn't. So it seems like maybe they're able to control at the center there which of the troughs is carrying a fluid. Having frequent loading, like if you have a really infrequent rotations, then you can have the pests growing more easily, and so there is a benefit to having like a big pulse of water coming through occasionally to try and wash away fly eggs and to scour off and to induce the sloughing. There's a table in the text that relates the loading rate in terms of kilograms per cubic meter of water per day and the depth of water that would be discharged for each pass of the filter. And so this is in millimeters per pass. And so each time one of those arms come through, if you have a really high loading rate, you'd maybe need to dispense as much as 600 millimeters of water per pass. And so that's pretty hard to conceive of, that almost a meter depth of water would be used for the flushing dose. But that's a pretty high loading rate. So the arms may be electrically operated or just operated with the inertia and momentum of the jet that's coming out, so dynamically driven or electrically. But they may have an uneven spacing, because if you look at the arm and the length of, okay, so if we have a circular filter like this, and here's the arm, and it's spraying, as it goes through, it's not tracing a very long distance, whereas at the outside end, that's moving at a much higher speed. It's all going at the same angular velocity, but the actual linear velocity is going to be greater at the outside of it. If it's going 1 revolution every minute, then towards the center, it's not tracing a very big circle. And so here in this picture, it's showing that the jets are spaced pretty far apart, close to the center, and then they get closer together towards the outside edge, just because that's what's required to discharge more water on the outside, since it's moving more quickly. So you have a greater flow per unit length at the edge of the distributor than you do towards the inside, just to try and even out how much water gets onto each part of the filter. And remember that the underdrains are in place so that the sloughing off of the filter media doesn't accumulate. If you had rocks all the way to the bottom, then it would sort of clog the filter media. And so instead of doing that, the underdrains and sort of keeping the rocks up off the bottom of the filter bed allows the sloughed filter solids to stay suspended. And 2 feet per second as a velocity is more than enough to keep the solids suspended. And then the other benefit of having the elevated underdrain is that it improves the circulation of air through the filter, and sometimes it may be necessary to do forced air venting, to actually attach a blower, maybe the kind of blowers that they have to fill up those like bouncy castles you've seen. It's something very similar to that. They'd attach a blower and just increase the ventilation to the bottom of the trickling filter. Increase the air contact to increase the rate of substrate removal. If it's a rock filter media that's being used, then it may be necessary to have really a pretty rugged and robust reinforced concrete support structure underneath the trickling filter. But the structural requirements are a lot less intense if plastic media is used in place of it. I mentioned earlier that sulfur in the wastewater tends to increase the odor problems associated with a trickling filter. And so especially if you have an active blower in place and you're forcing air up through the filter media, then that can really spread pretty unpleasant smells into the surrounding areas. Some of the materials, hydrogen sulfide is formed anytime there are anaerobic conditions in a wastewater, and so the hydrogen sulfide wouldn't be formed inside the trickling filter itself, but the hydrogen sulfide could be formed inside of a collection network where the wastewater is moving very slowly through a sewer pipe. Then it's possible that all of the dissolved oxygen is used in the wastewater, and then bacteria start to break down components in an anaerobic environment, and that's what will take and form hydrogen sulfide. So that can really have a rotten egg smell to it, and actually at high enough concentrations, hydrogen sulfide can even be fatal. It can overcome a person and they'll lose their ability to smell it after a few minutes. At first, hydrogen sulfide smells really bad, but then after a few minutes of exposure, the smell goes away, and it can overcome people. We all know what the ammonia smell is like. You know, you've used ammonia cleaners before. And then organic sulfides and mercaptans. Mercaptans are actually one type of mercaptan is what's used for odorizing natural gas and propane. And so if you've ever smelled propane before it's been lit, they intentionally odorize it just so that people can notice if there's a little bit of an unintentional release of it. It's a pretty unpleasant smell as well. So in the picture you can see that they've put a lid on the top of the trickling filter. And so inside the trickling filter, that arm is still rotating and wetting. We don't get to see it though because they put a roof and a lid, and inside that headspace above the filter is an activated carbon that is absorbing the odors that are, it's sort of like a gas mask, a reverse gas mask though. In this case, the bad smells are being captured by the activated carbon before the cleaned air is emitted out into the environment. Another way to do it besides activated carbon is to have a chemical scrubbing, which would be sort of like a spray of water just into the polluted air, and the water that's being sprayed has a mix of chemicals that react with the sulfur containing compounds. Or biofiltration would be the use of microorganisms that actually can take the sulfur containing compounds that have volatilized out of the air. They're probably a little less common for municipal wastewater. Activated carbon and chemical scrubbing would be the most common. In the secondary clarifier that's downstream of the trickling filter, the solids content is going to be a lot lower inside the clarifier because remember there's no sludge recirculation. And so in an activated sludge environment, you may have 2,000, 3,000 milligrams per liter of sludge solids, but the majority of that is because you're recirculating the sludge and allowing the solids to accumulate. But in a trickling filter, you're not recirculating the slime layer, and so the clarifier is already mostly water. And because of that, that's one of the many reasons that settling happens pretty easily inside of downstream of a trickling filter, is because there's no sludge that was recirculating, so you don't have it's not as crowded as the particles begin to settle. And you can see in the text there's an an upper range and a typical range of overflow rate versus side water depth, and that's how tall the clarifier should be in order to get the solid particles settled out before removing the water off the top of the clarifier. Another figure that was pretty interesting in the text is one that relates the removal of BOD to the loading rate. And what you can see is a relationship that says when you have a lower loading rate, you're going to have higher removal because it's like you're not overloading the filter. The water is being, the BOD in the water is being more completely removed because the bacteria at the bottom of the filter are basically desperate for substrate. It's not as easy for them just to use the simple carbohydrates that may be dissolved in solution, and so they'll break down every last bit of BOD that they possibly can at the low organic loading rates compared to the higher organic loading rates where you have a high loading rate, there's going to be less removal. And this little flat part of the curve says that once you get to a certain part, even if you decrease the loading rate lower and lower, you're not going to have any further improvement. That there's an upper limit to the removal of BOD through a trickling filter. Nitrification is pretty complicated and can be uncommon in a trickling filter, but what this figure shows is that in different locations, they've had wildly different results in the temperature effects of nitrification. And there's a big poultry operation in Central Valley, Utah, where trickling filters are removed for agricultural wastewater, and they have pretty effective removal of nitrates, and you can see that in other locations they've had 5 times lower the rate of removal, but the trend is always the same, that when you have higher temperatures there's higher rate of removal for nitrates than low temperatures. But even at pretty low temperatures, you know, at 7.5 degrees Celsius, that would be pretty cold for water, where, you know, the water temperature, it'll increase and decrease through the seasons, but there is some lower limit to the temperature that you can expect to see at a treatment plant, just because the water is coming from people's homes. And so when you discharge water to the sewer, it's at least as warm as your house, and sometimes warmer if you've been taking a shower or washing dishes. So by the time it gets to the treatment plant, it's still relatively warm. And what this shows is that there's some temperature dependency, but to go from, at typical 20 degrees Celsius, 3 grams per day of nitrate removal per square meter of surface area isn't so different than getting about 2.5 at 10 degrees Celsius. And so it's lower, but you still can get nitrate even in cold water, nitrate removal in cold water. This figure is illustrating recirculation and the variables that we use for calculating recirculation ratio. So you can see that the hydraulic loading rate Q, this is just the water flow rate that's going through the treatment plant, that in equals out. The flow rate into the trickling filter is the same as the flow rate out, but then a portion of that flow is recirculated, and that's Q sub R. So that coming out of the bottom of the trickling filter is the treatment flow rate Q plus the recirculation flow rate. And the reason why we recirculate is to improve the contact time and therefore the removal efficiency, to try and dampen the variations in waste strength and volumetric flow rate at night. You know, even if you just have to recirculate continuously, and if you just have a trickle of water coming in, you can continue to recirculate the water all night long, and you may be not giving the bacteria as much BOD as they'd prefer, but at least it's not drying out and going to be destroyed because it's dried out. And recirculation also improves the DO, because putting a very thin layer of water over the media improves oxygen transfer. And that's one of the reasons why it's so energy efficient, is that, remember the blowers that are used to try and put air through a diffuser and aerate in activated sludge? Those are using electricity, whereas just the pump that's used for recirculation may also use a little bit of electricity, but then it's gravity that spreads out the water and makes the layer of it so thin that the dissolved oxygen can transfer over the gas-liquid interface and get into the water that's actually trickling over the surface. And so you can have a high DO effluent even though your influent DO may be pretty low coming out of the primary clarifier. This is showing a two-stage filter in this diagram, and it's using the first stage as a roughing filter and the second stage as a polishing filter. And in the calculations we're going to do for the in-class exercise today, you're going to see how the efficiency of the first rock trickling filter may be completely different from the efficiency of the second stage, because the BOD concentration is higher in the first stage. And these are the equations that you're going to use in the in-class exercise for the rock filter media. In the homework, it's different design equations, and we'll talk about how these design equations are different from the homework design equations, because in the homework assignment, that third problem that you've got, that's actually a plastic filter media problem where you're working through the example in the textbook. But in this case, we're going to take a look at the removal of BOD through a rock filter. And this is a sequential reactor where in the first stage, the rate of the removal depends on the recirculation ratio. And this F is a recirculation factor that's calculated based on the recirculation ratio. So what you do first of all with the given flow rates, you're given a flow rate of the recirculation flow rate and the hydraulic loading rate through the reactor Q. So you find R. With the recirculation ratio R, you find the recirculation factor, and then that's when you can find the efficiency of the removal. And the removal efficiency is how you calculate the concentration coming out, the concentration of the effluent. 1 minus the efficiency multiplied by the concentration of the substrate coming in gives you the effluent concentration. Now, both of these equations are calibrated for 20 degrees Celsius. And if you have an example where the temperature is anything other than 20 degrees Celsius, then you have to correct for the efficiency using this formula here. And the practical effect of it is that when you have warm temperatures above 20 degrees, the removal efficiency gets better. And then if you have cold weather below 20 degrees, then that makes the removal efficiency go lower. So you're not going to be removing quite as much substrate as you initially were. Okay, so here's the in-class exercise. Let me hand that out to you. And you can, of course, work together on this one. What we have is a two-stage trickling filter. It looks like some of my... Yeah, okay. Just one little arrow got cut off from the drawing that in the handout I'm giving you. That the water exits the second one. So here in this two-stage filter, each of them has a diameter of 17 meters. We know the height of it, because it's a rock, this is an example where it's rock, is relatively low. 2.5 meters is the height of the filter. The wastewater flow rate is given. The recirculation flow rate is given. And we know the inflow BOD concentration, meaning the Cn, is 160. That 160 is the Cn just for the first reactor, though. So the water that's coming into the first trickling filter is 160, then it's going to be lower coming out of it. So what goes into the two-stage is actually going to have a BOD concentration of less than 160, and that's what you have to calculate through the example, is what's the effluent out of the first stage. And you'll notice that C sub E1 is in the formula for calculating the efficiency of the second stage. So this C sub E1 means the effluent from the first stage. And so you have to correct for temperature basically 2 times, since it's a 2-stage reactor. So I'd like you to try and get a sense for these calculations. I'll set out the solution to this in-class exercise on the table if you want to have a look. If you get stuck somewhere or want to just double check that everything's going as it should. So I will pause the recording and turn you loose on that. So here's the equation that you will need to use in the homework problem. You know, you've got 2 activated sludge problems on that assignment and 1 suspended growth problem. And in that homework problem, the third one, it's a plastic packed filter. And so the design equations are a little bit different. And in a plastic packed filter, this equation that's on, you guys are going to want to hear this for the homework. Well, maybe not. This equation is different from what's in the book because in the example, they go through and calculate K sub T. And here in this note it says that K sub T is the K20 that you get out of a table multiplied by the cross-sectional area. And so this is actually what you should use in the homework. Don't separately account for the area a second time. And then one other thing I'll mention about the homework is in the problem statement it says, I think that the specific surface area is 90 square meters per cubic meter of volume. But this equation and the example actually, it's based off of 100. So if you happen to notice that it said 90 and that example is using 100, just follow the example. Do the same thing that the textbook author does. But actually, the author made a mistake based on the specific surface area. So let's just talk about in general terms what it takes into account. Similar to the rock filter equations, it's incorporating the recirculation ratio, R. And then what you'll actually be solving for in the problem statement is the hydraulic application rate. So this lowercase q, you'll need to rearrange the equation to solve for q. And so here in the design steps, I kind of walk you through what you'll need to do on the homework assignment. The kinetics are a little bit more sophisticated in the plastic filter equation. You correct for the depth of the filter, you correct for the concentration of the waste, and then you also, in a separate step, correct for the temperature. So the example you just worked, you only corrected for the temperature. In the plastic trickling filters, there's such a wide range of possible filter depths that they don't assume the same K value regardless of filter depth in the same way that they do for a rock filter. Most rock filters are about the same depth because there's just a limit to how tall you can make them because they're so heavy. That's not the case in a plastic filter. And so this first correction that you need to do in the homework assignment, you're starting off with the assumption that for some filter depth, D1, and this table of values here that's provided in the book, this table is the kinetic factors at 20 Celsius for a filter depth of 6.1 meters and for a substrate concentration of 150 grams per cubic meter. So that's the BOD, this is the filter depth, and this is the temperature for this table. In the homework problem, you have a different BOD concentration, a different filter depth, and a different temperature. So you're going to have to make all 3 corrections to the kinetic factors. And so the first step accounts for the difference in the filter depth and the difference in the BOD concentration. So that's what this equation steps you through, is D1 and S1 are 6.1 and 150 respectively, and then D2, in your case, they say use a filter depth of 4 meters, and the substrate concentration, I don't remember what the BOD was. I think it was maybe 120, but I'm not exactly sure. It'll be in the problem statement. Okay. Step 2 here is correcting for temperature, and you already got a taste of that tonight, where you use the same 1.035 to the value of the temperature difference, where it's going to bring the kinetic factor so that there's more BOD removal when it's warm and less BOD removal when it's cold. And then finally, I've rearranged the design equation here in terms of Q. So this hydraulic loading rate, lowercase q, is what you'll solve for as one of the steps in the homework problem. Okay, so after you've done that, then the tower area is just the hydraulic loading rate and taking into account the flow rate Q. That's how you find the cross-sectional area of the tower. And then the volume, the packing volume, would just be the 4 meters of depth multiplied by the area that you find in step 4. And then the BOD loading rate is the inflow substrate concentration, S naught, times the liquid flow rate divided by the volume. So those are the steps for the third homework problem. And the only wrinkle there is the fact that in the example, it's based on a specific surface area of 100 square meters, and so just go with that, even though in the problem statement it tells you 90. Okay. Another kind of attached growth is something called a rotating biological contactor. And so an RBC, as it's also known, takes kind of a unique approach. It says instead of pumping the water to the top of a trickling filter, wouldn't it be more electricity efficient if we rotated a wheel through the water? That way you're not having to pump the water anywhere. You just put the water in a tank and then you rotate this circular wheel. It's going to use very little electricity to rotate the wheel. In fact, if you aerate the water by doing a couple of diffusers, you could have some vanes, some directional vanes, kind of like a paddle wheel effect, so that the rising air actually causes the RBC to rotate. So that part of the time the RBC is out of the water and part of the time it's submerged. What that does is the bacteria will grow on the surface of this media, and then when they're out of the air, they're getting contact with the air, and when they're down in the water, they're getting contact with the substrate. And so it's kind of a in a way, an improvement on a trickling filter because you're avoiding the necessity of recirculating the water. So here's a diagram that shows an RBC in action. A little animation. Let me dim the lights for that. Could probably play this one at double speed. So they fill up those slots with the same sort of like a plastic mesh that might be in a trickling filter, but it's lightweight enough that it can rotate around, and this motor doesn't need to be very large. They've even animated the slime. Can you see the green slime growing there? So when it sloughs, it'll go down into the liquid. There's, the same kind of principles apply, where you're going to have the growth of a solid, even though you had a dissolved BOD. The way that we want to purify the water is turn a dissolved pollutant into something that can be settled. And the slime layer that's growing on here and will slough off into the water, that settles very easily in a secondary clarifier. And so these can range between, typically 3.5 meters in diameter, 7.5 meters long. They don't rotate very quickly though, 1 revolution, maybe up to 2 revolutions per minute. So they're not spinning around really fast. One thing that's kind of nice here, you can see they've put it in a little Quonset hut. That can help control the odor. If you have it in an enclosed space, then there isn't going to be the same issue of offensive smells. And it's easier. That rotating arm in a trickling filter, it can be tough to get even wetting. But in this case, each one of the discs in a rotating biological contactor is going to get the exact same contact with the liquid and the air as all of the discs next to it. And so it's a lot easier to get even contact from one side of the contactor to the other. And so here it's showing that the typical design approach is to have a loading rate specified, a hydraulic loading rate and an organic loading rate, same as what we had with a trickling filter, where the organic loading rate is the mass of BOD per square meter of surface area of the rotating biological contactor, and the hydraulic loading rate is going to be cubic meters per day of volume of wastewater per square meter of surface area. And you can have nitrification depending on how anaerobic you allow the water down inside the rotating contactor to go. And so that's another improvement of an RBC versus a trickling filter, is that, remember, the trickling filter is just sort of passively aerated. There's air naturally ventilating in the voids of the media. But in the case of an RBC, maybe you only have it. This part is showing that most of it is not submerged. Only a small fraction of it is submerged down in the water. But if you have it mostly submerged, then there's going to be, as this goes through, sections of it that don't get above the water surface that would be ripe for nitrification. So nitrification, you have to have a lack of oxygen to have the conversion of nitrate to nitrogen gas. And so the part of the RBC down here, as this rotates around, it's never getting up into the air. And so you could potentially control the aeration, turn it off for a period, and as that RBC rotates, have the conversion of nitrate to nitrogen gas. You could never have that same control in a trickling filter, not to the same extent. So this is showing that the RBCs can be configured either so that the water is flowing along the same axis that the RBCs are rotating. So, they're rotating in this direction, and the water is flowing in the parallel direction to that axis of rotation, or it can be perpendicular, and the concentration downstream is going to be the lowest. And so if you were going to try and do nitrification, the place to put it would be towards the end, because that's where the nitrifiers can compete against the bacteria that remove carbonaceous materials. Who remembers the objective of step feed? This diagram at the lower left, it says step feed flow. And so what's the purpose of step feeding something in comparison to perpendicular flow, where it's the same configuration, it's the same reactor, 1, 2, 3, 4 RBCs, but why would you step feed versus not step feed?
Give the bacteria and those later chambers a chance to get the higher concentration of substrate.
That's right. Step feeding is going to give you more efficiency because we have first order kinetics, and the interpretation of first order kinetics is the rate of reaction is proportional to the concentration of the substrate. So usually up here, in the case of the perpendicular flow, the bacteria that live on this RBC, they love it. They're getting tons of food because they're first in line. They're first in line for the food. The wastewater coming in always feeds the first RBC first. And so the last RBC it's not very useful because it's not removing things very quickly because the rate of the reaction is low when the concentration of substrate is low. Step feeding makes it so this first RBC isn't always first in line for the food. It's spreading out the BOD over all three of these first three rotating biological contactors, and so all three of them have that same high rate of removal, and then it looks like they're not step feeding to the last one. So, you know, that could use this last RBC as a polishing or trying to do some nitrogen removal. So that's the reason for step feeding, is to try and make things more plug flow. When we were talking about reactor configurations, we talked about a perfect plug flow reactor, which is essentially a pipe, and if you have a little plug of some constituent that's reacting, as it travels through the pipe, the concentration is decreasing, and by not having mixing, a plug flow reactor is far more efficient than a completely mixed flow reactor, where it's the tank and you've got it stirred continuously, and so that as soon as the water comes in, it's spread out and it's all the same low concentration. The kinetics of a completely mixed flow reactor aren't as efficient as a plug flow reactor. Having, you know, it's a little bit counterintuitive, but what we're trying to do is we're trying to make this one plug flow reactor, this another plug flow reactor, and this a third plug flow reactor, and each of them will start off at the first part of it having a high concentration. And so you're trying to get more of the reactor into the mode where you're having a high rate of removal. Now in the case of tapered feed, what you'd have is both parallel and serial performance, where you'd have 4 reactors in the first stage because that's where there's the most BOD, and so you're gradually reducing the number of rotating biological contactors as the BOD concentration decreases. Now, the strange thing about this, though, is that if you really did, if all of these reactors were the same size, the water would be moving very quickly through the 4th stage, because, you know, if you have only 1 reactor, whereas in the first stage you had 4, if it spent maybe 1 hour in the first stage, the water would only spend 15 minutes going through the 4th stage, because, you know, time is the volume divided by Q. And so the amount of time it's going to spend in the reactor depends on its volume. So that's sort of the counterintuitive thing about tapered feed, is you might think that it would spend the most time in the 4th stage because that's when the concentration is low and that's when the kinetics are unfavorable since the concentration is low. But actually it's spending very little time there. So
How long is the wastewater spending in these tanks?
Yeah, it varies. The hydraulic loading rate is the guide to that. And so if you have, let's say, a flow rate like we had in Huntington, the kinetics of an RBC are about the same as activated sludge, maybe not as high, because in activated sludge you've got so much more surface area because the particles are really small and moving around. And so it could be like a day, you know, a 1-day contact time in the RBC, whereas in the aeration basin, the hydraulic detention time maybe was, you know, half a day in activated sludge. This is a design equation that the book presents on how RBCs are sized, and their performance is a function of the surface area of the RBCs. We won't go through and do the calculations, but this is just to give you an idea of, you know, what does the performance depend on. It depends on how many of the RBCs you've got, the total surface area, and the concentration out of each one of them. Okay, Now, in combined aerobic treatment, we're trying to get the benefits of both worlds. We're trying to have our cake and eat it too, by combining a trickling filter and combining a suspended growth at the same time as fixed growth. And so this is a picture of a really old trickling filter. You can see it's made out of stones, a stone wall on the outside of it. And combining together a trickling filter and activated sludge in the past was done for places where they were trying to retrofit a reactor. Let's say if they already had a trickling filter but it wasn't giving high enough effluent quality, then they'd put activated sludge downstream of it. Or maybe a trickling filter could be put upstream of an activated sludge system as a roughing filter to just get a really quick, high efficiency removal of BOD. The advantages of combining these two technologies together is you get the resistance to shock loads that can exist with a trickling filter. Remember, that's because the slime layer is so thick that even if the outside of the slime layer is damaged by a toxic material or a really high concentration of BOD, then the rest of the slime layer beneath that is unaffected. Size efficiency is an advantage because the attached growth is so effective at removing BOD for such a small footprint cost and energy cost, energy efficiency being one of the advantages as well. Also, the sludge settles really well in a trickling filter because there isn't any risk of a filamentous organism that causes bulking sludge, and so you get improvements in the sludge settling characteristics. And if you put together the activated sludge downstream of it, that's where you can get the possibility of a high quality effluent, because you really have more tools in your bag with activated sludge and nutrient removal. As much as I like a trickling filter because of its efficiency, you don't really have as much control over the removal of nitrogen and phosphorus as you can from activated sludge. So the next few slides we'll look at some of the typical configurations for combined treatment where they're putting both trickling filter and some form of activated sludge together. And the first one is called a trickling filter solids contact. And what this is a really large trickling filter and then a pretty small aeration basin. The small aeration basin is really just that the activated sludge part of it is kind of the minor component that's just doing further polishing. And so the activated sludge is the afterthought and the trickling filter is the main event in a TF/SC, trickling filter solids contact. What you'll notice is that the hydraulic retention time in activated sludge is very, very short, 10 to 60 minutes. And you know, in a more typical activated sludge, it could be half a day, maybe a day of hydraulic retention time. And so it's a very short contact time in the aeration basin. And the sludge solids solid contact time is also pretty low. You know, in typical activated sludge, maybe the median value would be 5 days for the solids retention time, but in the solids contact, it could be as low as 0.3 days. And so it's really, the aeration basin is the afterthought in trickling filter solids contact. You can have nitrification there because in the, like I said, the main event is the trickling filter, and so most of the BOD removal happens in the trickling filter, and so the aeration basin is where you maybe would have a lower concentration of BOD, and the bacteria that can convert ammonia to nitrate are going to do that in the aeration basin. But the flip side of that is having a small trickling filter and a large aeration basin. And so that's trickling filter activated sludge. And in the case of the trickling filter is just going to be a rough removal of BOD, and then the majority of BOD removal is happening in the aeration basin, along with the possibility of nutrient removal. 4 times the loading rate through the trickling filter compared to trickling filter solids contact. So activated sludge is the emphasis in a trickling filter activated sludge. They should call it activated sludge trickling filter rather than the other way around, since it's the activated sludge that's so important here. That's a misprint. It's not 25,000, it's 2,500. 2,500 to 4,000 for the mixed liquor suspended solids inside the aeration basin. And then a more typical activated sludge solids retention time between 2 to 7 days. All right. This is a unique type of trickling filter configuration, and here what you can see is they're actually returning some sludge from the secondary clarifier and injecting the sludge into the trickling filter. And I looked for some photos of an activated biofilter, and I wasn't able to find any using Google image search. But the book does mention that sometimes they have activated biofilters where the sludge itself is introduced into the trickling filter, and the filter media has to be pretty big in order to accommodate a sludge accompanying the primary effluent into the trickling filter. And so there is a specialized wooden filter media that's sometimes used, or if they use plastic media, it would have to be pretty large void spaces so that the sludge doesn't clog the activated biofilter there. So what's the potential disadvantages of this approach? It's that the sludge is going to put the possibility of clogging of the filter in a much higher probability than if you're not returning the sludge. So, not only are you returning the underflow, but you're also returning the activated sludge. And so you have the possibility of getting the benefits of activated sludge. Not only is there a slime layer inside the trickling filter on the media, but the water itself has suspended growth inside of it. So trying to get the best of both worlds. So what if we put one of those upstream of an aeration basin? And that's what this configuration is showing, is the biofilter that we saw in the last slide, where you are putting a sludge into the water that's going through the trickling filter, and then also having an aeration downstream of that. So that's the combination of biofilter and activated sludge. Now, here it's showing that you'd have a trickling filter and then having activated sludge with an intermediate clarifier between them. And we didn't see that in the previous slides, where it went straight from a trickling filter to activated sludge. And the purpose of having that intermediate clarifier is just that if you put the sludge solids from the trickling filter into the aeration basin, you're kind of losing out on some of the good settleability of the solids that come off of the trickling filter. And so this intermediate clarifier is always going to be like your A student, because the sludge solids settle really well coming out of a trickling filter. And so you get the benefits of everything that'll settle easily. You do that while you can, rather than introducing it into the activated sludge. And then the trickling filter solids that would have settled easily if they hadn't been mixed with the sludge, because if you mix them together, then in the secondary clarifier after the aeration basin, it's so thick with particles that the settling is more challenging downstream of an aeration basin than it is downstream of the trickling filter. The other benefit of keeping them separated, as it's mentioning here, is that you can protect the nitrification from toxics and inhibitors. So this first stage is a little more isolated from the second stage. If you're settling out the sludge and removing it, anything that was contaminating the sludge, like the type of industrial discharges that could cause damage to nitrifiers that nitrifiers are really weak bacteria and they're very sensitive to inhibiting substances. And so by removing this sludge, instead of letting it get into the aeration basin, you're sort of protecting what's living in the aeration basin, including if you have a nitrification step going in there. So this is showing some of the typical design parameters for trickling filter activated sludge in terms of the solids retention time of 2 to 7 days that we were looking at before, food to microorganism ratio, suspended solids concentration, and so on. How big the downstream activated sludge part of it is going to be based on how good the upstream trickling filter is. And you'll notice that none of the configurations we are looking at had the trickling filter downstream of activated sludge. It's always the trickling filter first, and then second is the activated sludge, not the other way around. And it's because the trickling filter isn't as effective at getting it all the way down to the limits for discharge. The trickling filter can take like the first crack at removing BOD, and then the activated sludge gets it the rest of the way there. And so how big the activated sludge needs to be is always going to be dependent on the trickling filter and not vice versa. The other thing I wanted to point out from this slide is that the trickling filter is more effective at removing particulate BOD than the activated sludge. Remember, the BOD is in two places. There's going to be some of the dissolved BOD that's in the water, and there's going to be some particulate BOD that's in suspended solids. Trickling filters can remove the particulate BOD because it's spending longer on the surface of the slime layer. And so that's another benefit of having the combination of the upstream trickling filter and the downstream activated sludge. So in this figure, it's showing the relationship between the BOD loading rate and the solids retention time. And so this is a classic relationship of the higher the BOD loading rate, the lower the solids retention time. And this you can use to estimate how much biomass is going to be generated in the trickling filter and how much has to be removed from the clarifier. And the other figure is showing how much needs to be removed by the activated sludge system, particulate BOD, PBOD versus SBOD. The particulate BOD is going to be really hard for the activated sludge system to remove, whereas the trickling filter can remove it more easily. Suspended growth doesn't have to be on a fixed material, though. A little foam cube, like is shown here, can be injected to an activated sludge system, and then you get some interesting benefits from having that foam cube. The bacteria will grow on the surface of the foam cube, and then on the inside of the foam cube, you'll be an anaerobic environment where oxygen doesn't penetrate as easily, and you can get some of the same effects as we saw with the granular activated sludge reactors, where at the center, since it's anaerobic, there's nitrogen removal. And so they call this an integrated fixed film activated sludge process. Integrated means that the media is put inside of the aeration basin. The difficult thing, though, is keeping these little plastic foam pellets inside the aeration basin. And so you have to have like a net or a mesh to make sure that they don't exit the aeration basin, because if they get into the clarifier, then having a bunch of foam pellets could clog the clarifier. So the main reason for doing this is improving nitrification by having a section of the cube that's anaerobic. And then denitrification can happen inside of an aeration tank. Usually denitrification has to be in an anaerobic environment, and so you can't do it in an aeration tank, and that's why they were cycling at the Huntington treatment plant turning off the aerators for a half hour, then turning them back on, going through that cycle of aerobic and anoxic. Well, you can leave the aerators on and simultaneously get the removal of BOD and the removal of nitrate with an integrated fixed film reactor. So this is showing a diagram of how they've got a screen here to try and keep the plastic foam inside the aeration basin. And they may have the recycle of water inside of the aeration basin, and they do have the recycle of sludge solids. But those little plastic foam pellets or cubes would take up maybe 20 to 30% of the reactor volume. And so there's still a lot of empty space, and since it's aerated, the air is being injected through a diffuser. That keeps them sort of mixed, and so they don't settle to the bottom of the reactor. You can increase the loading rates, and you can also increase the suspended solids. And so you look, the suspended solids concentration is quite a bit higher than it would be in a typical activated sludge, where maybe an upper limit would be around 4,000 milligrams per liter. By introducing those foam pellets, it provides a much more rich environment for the bacteria to grow on, and so the suspended solids concentration is a lot higher. Now, Captor and Linpor, those are just proprietary brand names for the cubes, and it's kind of funny that somebody would patent the size of a foam cube, but it's essentially what they've got is the patent on the dimensions of the foam and then the material that they've used. And if you've ever slept on like a foam mattress before, like memory foam, that's pretty similar to what these are like. It's just a viscoelastic kind of a plastic foam that they cut up and introduce into the reactor. So here's a look at the Linpor cubes, and what sets them apart from some other media that could be introduced is that they're pretty durable. Like they break down less than 1% per year. One of the problems with plastic is that if it's set in the sun, it gets brittle and can break down just from UV exposure. And so I think part of the research they put into Linpor is trying to make it so that it's resistant to exposure from UV rays, because a lot of aeration basins are just out in the open. They're not covered or shaded at all. It's buoyancy neutral, meaning that it has the same density as water, which makes it easy to mix the Linpor through the aeration basin, and you don't have to put a lot of mechanical energy to keeping them suspended. And it's easy to retrofit an existing aeration basin just by putting these in, and you have to configure a screen so that they stay in place and don't go out of the aeration basin. So it can be used to increase the capacity or improve the effluent characteristics. And I don't know, this is something maybe that they could consider in Huntington to get a little bit of more nitrogen removal. But it, you know, as he was talking about in the tour, they've just got so many million-dollar problems, whether it's the sludge incinerator not working anymore, or the million-dollar problem of the pipe degrading from hydrogen sulfide that comes in. Maybe you know, an add-on like this isn't in the budget. So this is a similar idea, the moving bed biofilm reactor. Instead of cubes, these are cylindrical polyethylene elements. It's a permeable piece of plastic that you put inside of an aerator. The difference here, though, is that you can see there's no sludge return. In the previous slides where we've been looking at, there has been return sludge into the aeration basin. And so what's unique about the coldness process, the moving bed biofilm reactor, is that you don't recirculate the sludge. It's just sort of like the foam plastic pellets that you put in here become the sludge. That's where the solids are, that the growth of the substrate occurs inside of the aeration basin, and there's no return sludge, no backwashing. Eventually the solids are going to be removed, but it comes out of the effluent, and so there's a clarifier downstream of it. there still is a clarifier. It's just that you don't have to put the sludge solids from the clarifier into the aeration basin. This is showing that if you wanted to cycle between aerobic and anaerobic mixing, you could have these pellets suspended by mechanical mixing instead of suspended by injecting air through a diffuser. And so having a mechanical mixer prevents them from settling, but you don't have to use oxygen to do it. And so you can have nitrogen, phosphorus removal if you have a mechanical mixer in there as well. This is showing that depending on how you put them in order, you know, like if you have some that are aerated and some that are not aerated, you can have the removal of nitrogen. So denitrification is the upstream step before aeration. You put the denitrifying bacteria first in line because they need the higher concentrations of BOD, but they don't need oxygen, and so the suspended packing with no sludge recycle doesn't mean you have no recirculation. Here you can see it's a liquid recirculation, not a sludge recirculation, and having the option for a liquid recirculation just ensures that during low flow periods that the volume inside the reactors doesn't go too low. It's also possible to put solid packing like you would see in a trickling filter inside of an aeration basin. And so what this diagram is meant to describe is if you had like a rigid plastic frame with little slots inside of it, if you put a instead of the free-floating little plastic pellets that are floating around, if you put a stationary surface inside the aeration basin for a biofilm to grow on, you can have the benefits of some suspended growth inside the tank and then fixed growth on the surface of the plastic. And so why would you want both? Why would you want to have some suspended growth and some fixed growth inside the reactor? It just seems more complicated. You're putting a new piece inside of an existing aeration basin. So what could be the possible benefit of that? Exactly. Remember, the fixed film, there might be 10 millimeters of bacteria. Only the outside part is in contact with oxygen, and so the bacteria on the interior are anaerobic. They're still in contact with substrate, and so the nitrogen can diffuse through that slime layer, but oxygen doesn't make it all the way into the slime layer. And so here you've got your anaerobic removal of nitrate inside of the attached growth, and then in the fixed growth area, then in the suspended growth area is where you're getting the traditional activated sludge effect. So there's so many different proprietary systems that do essentially the same thing. Here they were putting the filter packing into an activated sludge. Here in the Bio2 sludge system, they're doing the same thing. It's just that they're orienting them so that it's a vertical liquid movement. The aerators are at the bottom underneath the filter packing. And so they're saying in their proprietary system that putting the air diffusion underneath the fixed surface that the bacteria are growing on just improves recirculation through the packing bed, improves the removal of BOD. This is kind of a treatment system that's similar to a drinking water filter. In drinking water treatment, after the water goes through coagulation and flocculation, then it's put through a sand filter. And the purpose of that is that the flocks will impact into the sand grains and then they'll stick onto the sand grains. And so here it's a similar kind of effect in a way in that you've got submerged attached growth, and so the growth of the bacteria is on a packing material, but it's fully submerged inside of a tank, and it's going to need to be cleaned off occasionally because of sloughing. But what they're saying is that if you accumulate some water for backwashing, and then when you need to clean off the solids, you return the water the opposite direction that the water is usually going. Like normally the water is flowing down when it's being cleaned, but then when you want to slough off and remove the sludge solids, you reverse the flow, and then that's when it goes to the clarifier for removal of the solids. That's the proprietary name of that one is biocarbone. So Bio4 is also an upflow process. Biostyre, you can see the water is going upward, but here the difference is that they try and isolate an anaerobic zone first, anoxic, then followed by aerobic zone, and so they're trying to get nutrient removal, and then there is a recirculation step as you'd need for the removal of nitrogen. Finally, in the case of a fluidized bed reactor, you're having particles that if you didn't inject air would settle downward, but because you're injecting air, these particles stay suspended, and they allow a slime layer to grow at the top of the surface here. It's a biofilm that accumulates on the top of the bed, and so it's just kind of a unique way of not having to use a clarifier all the time, is that the biofilm is growing on the surface, and then they slough off when it gets too thick, and then it just floats to the surface and it stays at the top, and then they would screen it off in the same way that we saw like that moving conveyor belt at the top of the clarifiers at the treatment plant in Huntington, you know, by sweeping off the solids that float to the top of the surface there. Then it's just kind of a simpler way of removing the slime layer that sloughs off. So those give you kind of an idea of the exotic directions that attached growth has gone. If we just finish off by taking one last look at our announcements here. Next week is the homework 4 is due. The week after that, the research papers, and then we'll have our final exam on the 6th. So please send me an email or feel free to stop by if you have any questions on the homework. Other than that, I hope you have a great night.